So we're excited to have you, Sue, tell us about adaptive estimator selection for off-policy evaluation. Yi is a PhD student in the Department of Statistics and Data Science at Cornell University. While there, she's supported by a Bloomberg Data Science PhD fellowship. She previously received her Bachelor of Science with honors in mathematics from Nanyang Technical University in Singapore. Let's see, she worked as a research intern in the spring of 2019 at the machine learning group in Microsoft Research, I suppose where this work was done. And then again in summer 2020, she worked as a research intern at Bloomberg AI. Okay, do you want to take it away?
Oh, cool. Thanks, Daniel, for the intro, and thanks for having me here today. And I'm really excited to be here today to talk about our work on adaptive estimator selection for our policy evaluation setting. And this is based on joint work with Pavithra and Akshay from Microsoft Research. So let's get started. The talk is about reinforcement learning, so which we know that the agent need to actively interact with the environment to collect like useful feedbacks, which could help it to improve its sequential decision-making ability. And typically the long-term goal is to like maximize some notion of like cumulative reward. And this becomes more and more popular these days, especially with the development from this deep learning techniques. We see a lot of like empirical successes for RL these days. And for example, like we see like reinforcement learning algorithms, they could achieve like superhuman level performance in like Atari games, in playing chess, Go, and even in this like very complex video games. And there are like definitely like success of RL in other domains, but at this stage, it seems like most of the success we have like are happening in this kind of like game related domain. And mostly this comes with the fact that we have a good simulator, and also which makes it like cheap and feasible to collect like millions of trials of data. And however, if we think about like how to advance RL in this like real world applications, it seems like there's still a large gap between like those like empirical success. So because most, if we think about like the real world applications, most of them are like kind of like a societal applications. So if I take a few examples of it, if you think about like recommender systems, the agent need to like interact with different users, say like by recommending different products and trying to like explore what preference they have. And also like in healthcare, the system needs to interact with the patient and learn like what are the best like possible treatment that I could give. And beyond this, like reinforcement learning is also suitable tool for other like real world applications such as like educational agent, like robotics, dialogue systems, and etc. And typically in these systems, in this like different domains, like typically we do not have a very good simulator. And also, if you think about like online experimentation with human, it is typically very costly and also like could be infeasible. Because if you think about in recommender system, like if you're deploying some, like if you're doing some exploration, like using a bad policy, then it may lead to poor user experience and you may like have a high risk of losing this user in the platform. And also in some domain, like even this kind of like randomized experimentation could be like dangerous, unethical, or even illegal. And this typically happens in the domain like which the top priority is kind of like safety, and such as like in autonomous driving and healthcare. And these limitations in the online interaction in these domains motivates us to switch to the off-policy RL setting. So for which the goal is that instead of like interacting with the environment or with the MDP, we just learn to act by only using the past log data, which typically we collect them by as a byproduct of our previous like log of our previous system. And also this typically this batch data will come with a like large amount. And so basically, this plot shows like how on-policy RL compare with off-policy RL, which is the figure that I adapted from a very nice tutorial on this topic. And if you see in the left figure, it shows like in the classical on-policy RL setting, the agent is either given the on-policy data or or they could like interact with the environment by deploying the current policy, then so that they can collect like fresh and on-policy data and then use them to update the policy. And well, in off-policy RL, which sometimes we also call them like batch RL, which shows in the right figure of the plot, basically it employs the dataset D collected by some like previous logging policy, or we call behavior policy pi beta. And then the dataset is collected using this logging policy once, then it is frozen and like not changed or like being added during later like evaluation or training time. And basically, we do not interact with the MDP at all, and we only use this batch data to do like policy evaluation or learning problem. So formally define the problem setting we're working on. So it's basically like episodic RL with like horizon H. And the environment is characterized by this MDP, which we have state space S, and the finite action space A, and also the transition matrix P, and also reward function R, and also this discounted factor gamma. And the data we log is from a behavior policy, or we also call it logging policy here, which is denoted as pi L. And basically it maps the context to the probability simplex over the action space. And you can think it as just your like previous used system. And given this, the data generation process is given as follows. So we have the initial state S1 is chosen from some initial distribution P0. And also for the subsequent time steps, we draw action A according to this behavior policy or logging policy pi L. And then we receive immediate reward, like drawn from this conditional distribution R given R conditional state S and action A. And then we will translate to the next state according to the dynamic of this MDP. And therefore, like the data we collect is in this format. So for each episode of our past interaction that we collected and using policy pi L, we collect a trajectory have like H such tuples, and each tuple will compose of like SAR, which denotes as state action reward for different time steps. And the batch dataset D we have is just a collection of like n such trajectories. So our goal here is that we only want to use this batch data without doing some like online interaction with the environment, and to do like either policy evaluation or learning problem. So to define them concretely, so basically the all policy evaluation problem deals with the problem of trying to like estimate the performance of a new target policy pi t, but we are only using the batch data collected by a different policy pi L. And this policy evaluation problem is of great importance because typically, if you think about these different AI systems, they're like updated regularly to better serve the user. And if you want to deploy them in real world, it's better to have some like performance guarantee. And typically, this performance of the new policy is measured by this expected cumulative reward, and which we're drawing action following from this new policy pi t. So regarding to the downstream task of policy learning, it answers the question that how can we only use the batch dataset D collected under policy pi L and do not interact with the environment to learn the optimal policy pi star, which could give us the highest like performance or highest utility. Typically, off-policy learning will rely on off-policy evaluation as an important subroutine. And therefore, for today's talk, I will mostly focus on off-policy evaluation problem.
Sorry,
as I mentioned
I have
before,
a question. Yep. Can I interrupt you for a second? So is it going to be
yep.
important to use discounting in this setting? Because we have both a finite horizon and a discount factor, which is a bit of an unusual combination. Is using a non-trivial discount factor going to be important later on?
Oh, I think it's not that relevant. So basically, you can take gamma equals to 1.
I see. All right. Okay.
Yep.
Great. Thank you.
Yep. So as we just discussed like before, like this like limitation of doing online experimentation in different real world applications make off-policy evaluation a very like attractive problem setting. And it gains actually more and more attention these days, as you can see here, like there are tons of papers on this topic. And also like a lot of estimators are developed this 2 years like for efficient evaluation for policy values. So like there are a lot of estimators in this like field. And in general, if we think about like this like different all-policy evaluation estimators, they could be like categorized into these different three like domains. And it is shown in this figure, which I adapt this figure from this nice paper by Voloshin et al. Like it's a very nice paper who study like how different like all-policy evaluation methods perform in the real-world application settings. So basically, as you can see here, like we have this kind of like two orthogonal regime. And one is the inverse propensity scoring based estimator, and which is also known like importance sampling. And the another family of estimators is called direct methods. And the main distinction of this class of estimators compared with the IPS method is that it focused on using regression-based technique to directly estimate the value function or Q function of our target policy or evaluation policy. And the third regime, or the most advanced regime, is this kind of like hybrid methods, which, as the name suggests, that it's trying to like efficiently combine the IPS-based approach and method-based, like model-based approach. And also, as you can see, there are a lot of estimators like described in the figure, and the relative position of these estimators are basically reflect like how close they are, how close that they are related to different regimes. So I will very briefly discuss this like two orthogonal category. Like one is IPS-based method, and one is like direct methods. And you could refer to the literature for this. Like there are a lot of literature on this. If you're like want to know more detail. So the first category is like this IPS-based method, and basically the key idea is that they reweight the data from the logging policy by the importance sampling ratio, and the importance weight is just like is a ratio like how likely it appears in the new policy divided by like how likely it shows up in the logging policy. And typically this weight like involves like the product of T like ratio terms, and which could blow up the variance of the estimator. And there are also like a lot of variants of like IPS developed in this regime. But in general, like this class of estimators, they suffer from large variance, which could be like exponential in the time horizon age, which also known like the curse of horizon here. And the good thing is that this class of estimators, they're typically unbiased under very mild assumptions, like propensity is known, etc. Or they have very small bias. And the other orthogonal category is this direct methods, which they try to directly learn the Q function of the new policy. And typically learning this Q function, like with, basically we use like function of approximation to learn this Q function. And typically the approximation error in this learning this Q function will directly translate into the large bias in this final, like in this overall estimator. So this class of estimators, typically they suffer from large bias, but typically they have like smaller variance compared to the like IPS-based approach. So they have like distinguished properties for the bias and variance. And the more advanced estimators is like less in this hybrid regime, which like they try to like efficiently combine the weighting-based or IPS-based method and also the direct model approach. And I will just introduce, very briefly introduce two examples here. One is a very popular like W robust estimator, and for which they rely on the estimated value function V hat here as a baseline. And they use the importance sample weights, which is a rho term here, to adjust like how the observed reward deviate from the baseline. And this estimator is unbiased when we know the propensity. And it basically uses this like, kind of like a baseline, or we call control variate, to reduce the variance of the estimator. But it still suffers from the curse of horizon issue because it still make use of this like large importance sample weights. And the other example in the hybrid domain, I think it's which we will discuss a lot today, is called the partial importance sampling estimators, and it's a set of estimators. And this is initially proposed by Thomas and Bronskill in 2016. So basically, it mixes the IPS-based approach and direct method-based approach in a more strict way. So the rationale behind this set of estimators is that if you think about IPS-based estimator, they typically suffer from this kind of like exponential like variance, which scale with the time horizon. So how about we just use IPS for like small time horizon, for say like for the previous eta time step. Then for the like the reward like we collect after time step eta, we're trying to estimate it using any direct model-based approach or value-based approach. So since we are now only using this IPS-based approach for only eta time step, which is maybe much smaller than the time horizon h, so this will help us to reduce a lot of variance, but we may increase a little bit bias because we're utilizing the value-based approach afterwards. So this is one concrete case where we use the per horizon IPS as a specific estimator in the previous eta time steps. Then we switch to direct model from eta plus 1. So as you can see here, when eta equals to 0, basically we're back to the direct pure model-based approach, which we know that typically have large bias but small variance. And when eta equals to h, we're only using the IPS-based approach. We know that we have small bias but large variance. So as eta increases, we're putting more and more steps or more and more rewards to estimate using the IPS-based term, so which increase the variance but decrease bias. So basically, we could expect this trend drawing in this figure here, that as eta increases, we have increased variance but decreased bias. And also we observe that this parameter eta, which we call the false horizon here, it kind of control the bias variance trade-off among this set of estimators. And also a specific case in this class of estimator is called magic, which they just replace the previous eta time step using the weighted W bus estimator. Yep. So any questions up now? Yep. So as we have seen that there are a lot of estimators developed for off-policy evaluation. Well, most of them are built upon pretty solid mathematical principles, and they share different theoretical properties. From a practitioner's view, we may face the question that if I have a specific application case, which estimator should I use for my specific application? And the paper by Voloshin et al., as I just mentioned, they give a very comprehensive empirical study for a wide range of estimators. And this figure basically nicely summarizes their empirical findings. And they give a very general guideline about which model class should I use for my specific problem. So basically, you need to go through this decision tree, and the final recommendation depends on the key factors in the node, where whether you have severe policy mismatch, what's the horizon length of your problem, etc. With these guidelines from the literature and as well as some domain knowledge, we may have some idea about which class of estimators should we use. But does this solve the estimator selection problem? The answer is no here, because we may observe that we have a second selection problem arises. So as many estimators themselves, they have hyperparameters that must to be tuned, such as the false horizon eta in the partial importance sampling estimator. And in most cases, these estimators, they moderate a bias variance trade-off, in this partial importance sampling based estimator we just discussed. The eta parameter here, they control kind of the bias variance trade-off. And also, this is also observed empirically, as mentioned by in this empirical paper. They observed that empirically, the index set for hybrid methods such as magic, they have large impact on the performance of the method. Also, in some possibly indirect way, the hyperparameter not only affect the evaluation accuracy of the estimator, they also affect this kind of downstream learning performance. And this figure is adapted from the Retrace Lambda paper, where the author they studies that how different lambda factor used in the algorithm could affect the performance of the learned policy. As we can see here, that this lambda is pretty critical to the performance of the learned policy. And even though this paper they give some heuristic on this, such as for Q learning, it's better to use lambda equals to 0.5. But it's still an open question on how do we select this hyperparameter effectively and in a more systematic manner. So when we face the problem of hyperparameter selection, we may think about the cross-validation as a pretty natural fix. However, this is not the case for off-policy learnings of off-policy evaluation setting. The main issue here is that we never have on-policy data. And though the validation set exists, it only appears in the form of like off-policy data. And evaluating the performance of different estimators in the validation set, it is again an off-policy evaluation problem, because we do not have like unbiased and low variance approach to compare like different estimators. And motivated by this, so we studied the estimator selection problem for the off-policy evaluation setting. And in a very brief summary, that we provide a very general technique, which called like selection by Lipschitz principle for off-policy evaluation, which also called like SLOPE. And as name suggests, this method is motivated by Lipschitz principle, which is initially proposed for bandwidth selection in non-parametric statistics. And theoretically, we provide the oracle inequality, which guarantees that our estimator selected by our procedure is pretty competitive with oracle tuning. And empirically, we see that it also outperforms standard baselines, such as like in this like 2RL environments, like SLOPE has much smaller mean square error than either like model-based approach or weighting-based approach. And the most like interesting is that no matter like model wins or like weighting-based approach wins, SLOPE is like always competitive with the best approach. So before I introduce the selection principle, I will formally define the problem of like estimator selection problem in a more like abstract or general way. And then I will use like two case studies to make them more concrete. So to begin with, we have like some population lies in this abstract space Z, and we have a distribution of this population D over Z. And we would like to estimate some parameter theta star, which is a real valued function over our population distribution D. And the data we have is like IID from this distribution D. And we use D hat to represent the empirical measure. And to estimate this parameter theta star, we assume that we have a set of M different estimators that we want to select from. And given the data set, we form the estimate theta hat I, like by only using the data we have. And among this like M different estimators, we would like to choose the index that minimize the absolute error of like theta hat I minus theta star. So basically this like this oracle index depends on the unknown parameter theta star. So it could not be computed from the data. So our goal here is trying to find some like data-driven approach that we could find some like index I hat could approximately minimize this error.
Can I ask one question on that slide? Sorry.
Yep.
Is it important that you define I hat to be the best thing in hindsight rather than the best on average over draws of the data? Like I would have imagined there being an expectation over D hat in the definition of the best index. Does that distinction matter or not really?
So you are saying that we are trying to define I hat as the empirical kind of empirical best estimator, or instead of like
Yeah, that I hat is that's right. It's the best. I mean, it's a random variable because it depends on the draw of the data set. And you might have imagined that you have it being the best in the population or something.
Yep, I think this one is. I think the one you propose is kind of more relaxed version of this one.
Yeah.
Yep.
So that distinction doesn't matter
I think
much
this is
for what's coming. I guess is.
Yep. But I think typically, like in like OP literature, people are compared with either the best estimator, either in mean square error or in this absolute error. Like this is kind of like a normal like criteria for compare different estimators.
Okay.
But I do not see a big issue here. Yep. So to make this like more concrete, like I will so let us use the previous OP in reinforcement learning as a running example. So in this case, Z is the space of possible trajectories, and D is the trajectory distribution collected by acting based on this logging policy pi L. And our goal here is to estimate this theta star, which is the policy value of our target policy pi t. And the data we have is collected from different trajectories by running pi L. And the finite set of estimators we have is this like partial importance sampling estimator, which have like different false horizon eta. And also the I hat is that we want to find the optimal false horizon, which give us the best estimation performance. So now we are going to introduce our methods, but before we go to the exact details, we need to make sure that our estimator satisfies some like property, and only under this like property or we say assumptions, we can provide some guarantee of our proposed method. So first, let us define this like theta I bar as the expectation of theta I hat. And then we can decompose this error term into the bias term and deviation term. So for the bias term, typically this is unknown because we do not have access of the theta star. But we will assume that we have like sharp upper bound on it, though we do not need to access this upper bound, and also our algorithm do not use this upper bound. And for the deviation term, it only involves this kind of like statistical fluctuation, so we can use any concentration argument here to find a high probability upper bound. So this part should be easy to get. And we call the existence of these two upper bounds the validity assumption that need to be satisfied for our the set of estimators. And beyond this, we also need like kind of some monoticity structure on the bias upper bound and also on the confidence, that is the deviation upper bound. So basically, we need our estimators should be ordered in a way so that the bias upper bound is kind of like monotonely increasing. And also the confidence is kind of like decreasing, but not so quickly. And this is controlled by this constant kappa here. So this assumption actually is quite natural if we think about the partial importance sampling estimator that we just mentioned. So like we know that as eta increases, we can have this high increasing variance and decreasing bias. So we can just reorder this eta reversely to get our estimator set satisfy this monoticity assumption. And also for the rate kappa here, it is also straightforward to enforce it by just selecting the parameter set like appropriately, as we will see later in the example. So after introducing these assumptions, well, we could formally introduce our selection procedure, which is very simple, and it only utilizes the confidence bound. So here it is. So the first step is that we want to construct an interval for each different estimator. Like the interval is named like I here. And so the interval is basically the point estimate theta I hat plus or minus twice of the confidence at this point estimate. And after we construct intervals for each estimator, then we want to select the largest index, such as the intersection of this interval with all the previous intervals are non-empty. And also the final estimator we use is just this theta hat I hat, which based on this index. So for better illustration, I will illustrate using a example here. So as shown in this figure, we have like 5 different estimators, which give you like five different point estimates given data. And here is like theta hat 1 to theta hat 5. And we order the estimators in a way such that the confidence of them will shrink as index increases. And this is to satisfy our monotonicity assumption for the confidence. So basically, as we can see here, the interval are getting like smaller and smaller. And also like we build this interval by like plus or minus twice of the confidence. And then we want to choose index like according to our procedure, which is the largest index, which still have like overlap with all previous intervals. Here is just like the index 3 here. And this is pretty simple. And I will briefly introduce like a very the intuition of this method, which do not like take account for correctness, but I will provide a formal proof later. So the intuition for this method is that we need to we think optimistically about the bias term. So typically we're starting with some like unbiased estimator in the most left. So with like bi equals to 0 in the like theta 1 hat. And if we think this like optimistically, it is possible that we may have this bias term equals to 0 for all the indices before I hat, because this intervals like they overlap, and we could like take any element in the intersection and treat it as theta star. So it could happen that theta star lies in like the intersection of all the intervals. And so now we have like bias equals 0 for all the term before I hat. And then we definitely want to pick the one which give us smallest confidence. Then that is definitely like I hat, which is theta 3 hat here. And also, so for the index like larger than like I hat, say like for theta hat 4 here, basically we know the bias is non-zero. Otherwise, the confidence interval should like overlap with all previous intervals. And also after this like theta hat 4, we can see that the bias is starting to dominate, because as you can see, we can see that the bias 4 plus confidence 4 is larger than the twice of the confidence 4 here. So since like confidence, like, so we know that from this bias start to dominate, and since bias like keep increasing, but like variance keep decreasing, but like they're not decay so quickly, so the later indices may not be much better than the theta 3 here. So this is just a like very like brief intuition, but I will provide a correct proof like after this. So I will first introduce the formal guarantee that we have for this selection procedure. And it's in the form of this oracle inequality, basically, which guarantees that the selected estimator could compete with the error bound of the best estimator in the set that we're considering. So, and they're worth off by a constant factor, which is like 6 times 1 plus kappa inverse, and which kappa, we recall, it is the decreasing factor of the confidence term. So we need to point out that this like oracle inequality is kind of weaker than the ideal guarantee we want, because this is not compete with the true error of the best estimator we want. It is compete with the error bound. So, but empirically, we found that it gives pretty competitive performance. And a few remarks here is that and it is actually the first like oracle inequality for estimator selection of policy study. And so, well, previous approach such as like bound minimization based on like minimizing some mean square error, they can compete only with unbiased estimators, while ours can compete even with the biased estimator. So now I will give a simple proof for the theorem. So for this like oracle inequality. So to begin with, like we recall several notation first. So
I'm
here
sorry
we recall I
to
had.
slow you down again. Can I? Well, one other question is, can you comment again on why there's a B of I instead of a bias of I? So
Oh yeah.
I'm having trouble understanding, because you don't actually use B of I in the algorithm, do you?
Yeah, we do not use BI in the algorithm. We only use the confidence. But because we are not like know the theta star, so we cannot like exactly quantify what the bias is. But we are trying to say that we assume like we have some like upper bound of the bias. That is what BI. So this is kind of a more relaxed like assumption that we have in like compare with knowing the exact bias.
I guess
so
maybe
sometimes
you can increase. Like you can arrange for the upper bounds to increase while the actual bias may be going up and down.
Okay, so if I can be the min read that after. Okay, I see that point, John. That makes sense.
Yep.
Thank you.
So, yep. So, so basically for a brief notation, recall on the notation. So I had is index select by our principal, which is the largest index, which still have like the all previous intervals. And also we will use I star to denote the best index that we hope to find. And also we will introduce one like reference index, which is I tutor here. And this is the largest index, such as like the bias is still smaller than the confidence. And after I tutor, the bias is starting to dominate. And this reference point is kind of like have a kind of good balance of bias and confidence. And our proof basically they compose of two parts. The first step is that we want to show that I hat is pretty competitive with the reference point I tutor here. And also the second step is that we want to show that this reference index I tutor is competitive with I star, the best index. And combine these two will show the oracle inequality. And now we will show the first step is that we want to show that the error of I hat is competitive with the error of I tilde. And by definition of I tilde, which we know that it is the largest index that confidence still dominates bias. So by the increasing confidence of bias and decreasing trend of, by the increasing trend of bias and decreasing trend, increasing trend of bias and decreasing trend of confidence, we can easily see that for all the index I smaller than I tilde, which is in this blue region, we have like the bias is always dominated by confidence. So the absolute error of like theta I hat minus theta star, which bounded by bias I plus confidence I, is less than twice of the confidence I. So for the odd I in this blue region. And since we construct our interval as the point estimate plus or minus twice of the confidence, we know that the true parameter theta star must lies in all the intervals for all the intervals I for I smaller than I tilde. And because like recall like I hat, like the index select by our procedure, it is the largest index that have overlap with all previous intervals. We know that I hat is definitely larger than I tilde because for like we just showed that theta star belongs to all the intervals like I smaller than I tilde. So I tilde also have like non-empty overlap with all previous intervals. So also we know that the interval of I hat and I tilde they overlaps. So this means that there exists some point in the intersection of like the interval of I hat and I tilde, such that the distance from X to the point estimate is bounded by the corresponding confidence. And then we know that theta I hat is not far from theta star, because theta star is not far from this I tilde, where the interval of I tilde and I hat overlaps. And by this triangle inequality, we can bound the distance between theta hat and I hat and theta star at 6 times of the confidence at I tilde. So basically, this step shows that I hat is pretty competitive with I tilde. And in the second step, we want to show that this reference index I tilde is pretty competitive with I star. And this basically composed of like 2 different cases. So for the first case, if like I star is smaller than I tilde, which lies in this blue region, since the error of like I tilde is upper bounded by twice of the confidence that we just showed, then by the decreasing property of the confidence, it is upper bounded by twice of the confidence of I star. Hence, it's further bounded by the error of I star. And for the second part, if like in the second case, like when I star is larger than I tilde, say like when I star lies in this like pink region, we know that the bias of I star is upper bounded bias of I tilde is upper bounded by bias of I star in this case. So we only need to bound the confidence of I tilde. So since we know that I star is larger than this I tilde, we know that the bias of I star is larger than the bias of I tilde plus 1. And since after like I tilde plus 1, the bias starts to dominate. So we know that the bias of I tilde plus 1 is larger than the confidence of I tilde plus 1. And it's further like lower bound by the kappa times the confidence of I tilde, which is from the monoticity assumption. So combining this two that we, so combining this like the two like results, we have like the this oracle inequality like in terms of the distance from theta hat I hat to theta star, which is upper bounded by 6 times 1 plus 1 over kappa times the best like error bound we can hope for in the set of estimators. So is there any question for the proof?
Yeah, Chaba had a question, but I don't know why he's shy to ask it, which was about can conv I be random? So like, can these confidence bonuses be random? Chaba, go ahead and maybe you can
yeah, I can explain this. Yeah. Well, I was just basically wondering about whether, like, if this confidence intervals had database, like they're based on the data, they're random, then I could maybe just like take all these indices, order them so that the confidence intervals are decreasing, and then define this bias upper bound, as the least upper bound on the actual bias, which is unknown, that is increasing. And then the theorem is going, like, the question is the theorem going to hold for this random ordering of things, or is it just like it was important that doesn't happen? I should have paid a little bit more attention to the proof than I would know. I'm guessing maybe it doesn't matter, because like these were just like trivial, I mean, like not trivial, but it's just chaining inequalities, right? Like we didn't do anything with like on this event, on that event, like, oh, like, okay, this confidence intervals capture the true data, then yeah, it didn't matter whether they were random, and then the ordering can be changed in this way. And then basically you have a result that is always applicable. It just
So I'm a little bit like confused.
Yeah, I'm
what
trying to think about whether you can essentially make this result true without any assumptions by just pre-processing the data a little bit.
So like a confidence interval that would be random is if you divide by if you compute the standard deviation from the data itself, rather than knowing it.
Yeah. And then
I
just
see.
periodic indices, yeah, so that the confidence intervals are decreasing, and I define the bias to be appropriate for your assumption. It's an unknown quantity anyway, so it's going to appear in the bound only. And then the bound for this definition of the bias.
Yeah, I think with high probability it still holds if you like trying to just order the variance based on the like say some empirical variance that you calculate from data.
So it's very
basically
cool.
You can try.
Cool. Go. Yeah.
Yep. So I think yep. So this is just like we're going back to the partial importance sampling estimator that we discussed before, like to see how Lapsky like principle work in this case. So the set of estimators is like this different like partial importance weighting estimator, which we have different false horizon lengths. Like it ranges from 1 to h+1, and they're like in total h+1 estimators here. And as we can see, we have this like special case with like theta hat 1, which equals to like this pure IS based method, and this like theta hat h+1, which is pure like direct method. And we also see in this example, we have this kind of like bias increase and variance decrease trend as I increases in the set of estimator. So it's naturally satisfied this. And so if we assume the reward is bounded between 0 and 1, we can derive the following like upper bound for the bias. And also we can have this like high probability argument using like bursting for the confidence. Then it's also easy to see that the bias upper bound is increasing as a function of I. And also the confidence is like decreasing as a function of I, because as I increases by 1, we have like one additional term, like one less additional term to add on the summation. And the other thing that we need to verify is that the confidence do not decay too fast. So recall that we have this like kappa parameter in our monotonicity assumption. So after some algebra, we could show that the confidence do not decrease faster than 1 plus gamma times P max inverse. So P max, which denotes the largest importance sample width across all the state and action pairs. So basically combining this, we can have this like informal theorem for the specific setting, which we know that in this setting, if we select using Lapsky's principle, the oracle inequality is satisfied with this constant kappa equals to 1 plus gamma times P max inverse. And so to showcase the empirical
regarding the previous slide. So here, getting back to my earlier question on gamma, so this bound and the bias, this doesn't seem very useful when gamma is 1, right?
Oh, I see here. Yep.
As a 1 over
So
1 minus. But I suppose in that case, it can be really just replaced with essentially h, right? Or what?
Yeah, in that case, you have a very loose bias bound instead here, like you have this decrease rate in terms of gamma. Yeah, but the bias bound is kind of, even though this bias bound is kind of loose, but the main thing is that or Oracle guarantee can is in terms of the minimum possible upper bound for bias. It doesn't depend on which bias bound that you calculate here. So it could adapt to any bias, the lowest bias bound.
Right, but I'm still wondering if this can be worked out for gamma equals 1. Like what would this look like? Like h minus I maybe instead of exponential in I.
Yeah. So basically, the bias is only from the value-based estimate that from the time step I afterwards, and I can only think of very crude upper bound by say h minus I here.
Right. And then I guess my other question is about this P max. So this P max, is this the largest importance weight ratio? Right. So the supremacy they were taken over all state action pairs, not just the ones that were actually seen in the trajectory. So just trying to find out whether this is again a random quantity or something that's fixed.
I think it's a population version quantity that over all the state action pairs.
Right. Yeah. But then I would be concerned that this can be really, really big.
Yep.
Okay.
Yep.
Okay, good.
So the later part is more for the experiment that we're trying to do this partial importance sampling based estimator by over a lot of different conditions, which they differ in the horizontal lengths, in this different domain, which they differ in horizontal lengths, whether they have partial observability, and also the dynamic of the system. And the baselines we compare, one is the pure direct method-based approach, and one is weighted W robust, which is an instance from the importance weighting-based method. And also we compare them with MAGIC, which proposed also by Thomas and Brunskill. And basically they trying to find the optimal aggregation of different partial importance estimators by optimizing a surrogate for the MSE upper bound. And also we compare with our estimator selection procedure. And so basically these two plots, so the left plot shows that aggregately, this kind of aggregate performance of our method over this 106 conditions. So basically we draw the empirical CDF of the normalized mean square errors. And so for each for each X value, the corresponding Y value is how many conditions that estimator has the MSE at most X. So the top left, the graph, the better. And we can see that MAGIC have the overall best performance, slope have the overall best performance. And in the red plot, we compare this we do this statistical comparison for each pair of the methods. So basically, we have this kind of pairwise comparison matrix. So each entry, IJ entry, shows how many fractions of conditions that our method I beats method J here. And we can see clearly that for every pair method, slope always doing better than the other one. And also we so this is an interesting interesting experiment that we want to dig into detail about how slope select different indices. And so this is a special domain that developed especially to study this partial importance sampling estimator. And this domain has horizon 22, which it is basically a combination of two different domains. And the first domain is this kind of a model field domain, which you have a partial observability here. So which means that in this model field domain, that a direct model typically is not like that expressive for you to learn the value function for the first 2 time steps. Then after step 2, you switch to this model win domain, which like you can easily get a good value estimator afterwards. And in the red plot, we show the learning curve for the specific domain. And as we can see that when the number of sample size is small, we have the blue line, which is a direct model. It have pretty good performance, the model based. But the performance does not like become that much better as increases because it have this bias issue. And if you see the orange line and the green line, which is the weighted W robust and the magic estimator, they kind of like improves like, and also come like being better than the model-based approach when n becomes larger. And also slope is like kind of like in this red line is kind of like pretty like achieve pretty competitive performance no matter what the sample size is. And the interesting thing is that if we examine like which like time horizon eta, this false horizon eta that slope peaks, it like peaks like eta equals 2 nearly like 90% of the case. So which eta equals 2 just like the times that we're switching from this model fail domain to the model win domain. And also we like, I think I will not introduce it into detail, but we also like also using our Leipzig's principle to work on this like bandwidth selection in the continuous contextual bandit problem. So we need to select this hyperparameter H, which controls this different bias and variance trade-off. And also it have like pretty like competitive empirical performance also. So, and I would like to like end my presentation maybe here by in summarize like what we address in the off-policy evaluation problem and what like we are still like also some limitations that we do not address. And I think this will serve like as like important future work for this field of research. So the first thing is that our selection procedure slope, it addresses the problem on like how do we choose the best estimator within a class, and for which we know like qualitatively like how roughly bias and variance changes. But it do not address the problem like how do we choose among different estimator classes. Say like if we have like two model-based approach, one is get using like fitted Q evaluation, one is like we get by using some like model-based approach. So how do we like compare this estimator from different classes? And also it do not address the estimator selection problem, which we do not know how the hyperparameter affect bias and variance like in a clear trend. Like we do not know how it kind of qualitatively affect this. And also in theoretically, like our selection procedure guarantees that our select index is competitive with the best estimator, but in terms of an error bound that we see, like in terms of the bias upper bound plus the confidence. But it does not guarantee like our selection procedure is competitive with the best estimator in terms of the exact error that we want, that is the exact bias plus like confidence. So we're only compete with the upper bound and not the exact error. And also our procedure basically is like studies like how do we select the best estimator for off-policy evaluation setting. But like we're not like, but it's still interesting to see that how this could be like further utilized for other like downstreaming tasks, such as like off-policy learning study. Yep. So I like to end my presentation here. Yep. Thank you.
All right, thank you. That was very nice. I don't know if you saw, but a couple of us were like trying to clap a little bit, but not to make too much noise. So, so I have a couple of questions. I guess the most obvious one is, how does this whole procedure makes actual use of this whole reinforcement learning structure, this kind of episodic MDP structure of the problem? Because this whole Levsky's method that you described, which is a very nice introduction to Levsky's method, I have to say. So this is actually very general method, and this analysis that you've been explaining works very generally. So I'm just wondering, like, what is exactly the point where you make use of the MDP structure, and would it be possible to somehow make better use of this MDP structure in this kind of method?
Oh, I see. I feel like the I'm not sure how the MDP structure affects this, but I feel like RL is a natural like fit for this kind of method is because we have this kind of like there's naturally this kind of two regime of estimators. Like the weighting based approach, they have like this kind of like curse of Poisson issue. It's kind of like a result from the MDP structure because like you have this kind of like the product of ratio terms, and it's naturally like gives you kind of like increasing variance, like this kind of like natural trend for this estimator design.
Yes, right. I can see how this is very well suited for this method that introduces this false horizon, right, and uses like combines two estimators like that. But I'm wondering like how much further could you push this idea? For example, like in every step you could be using a different look ahead horizon, and you could have like a more complicated parameterization like that. Is that something that you think could work? Or maybe it would be like sort of difficult to do this ordering over the estimators if you do more complicated parameterizations.
Yep. So I think it's not like, so as I just like as I mentioned before, it's so for like retrace lambda or like Q lambda, when you have this kind of like return based algorithm, you still have this kind of like lambda term involved, which also controls kind of like a bias variance trade-off. So in that case, I feel it still could be utilized in that setting, which like not only like for this partial importance sampling based estimator. Yeah, because they're trying to correct like for like later different time steps, they're trying to like adjust the reward by the importance sample ratio. And they're for retrace lambda, they're doing the max minimum of this like importance ratio and also the constant one here. So I think it could be also utilized in this different settings, which you are trying to look ahead and by discounting different future time steps.
Right. I see. Thank you.
Yassine, you have your hand raised?
Yeah, so I have a question. You had this IID data assumption. I'm wondering how crucial this assumption is. And like, can you handle more adaptive data collection?
Oh, I see.
Or which part of the proof breaks down actually?
I think in general, we do not. I think in the proof, actually, we do not rely on any ID assumption as far as I see here. As long as for non-ID, if you can characterize the bias and variance, this trend like more clearly, but it's more easier for ID setting, I guess.
So if my data is such that, favors one of the models, I don't know.
Yep. Sorry, I'm making something. Yeah.
Yeah, thanks. I mean, that was it.
Yep. I think, yep, just as Akshay said that it's as long as even for like non-ID data, if you characterize this like confidence and bias like structure clearly, it should be fine. And it do not utilize this IID setting.
Can I ask a bit about that? So it does seem that one constraint to really using this in practice is that you need to be able to, it would seem that you need to be able to tightly characterize the confidence bounds. But when you run these numerical experiments, I guess that the confidence bound you flashed has things like p-min in it, and maybe I would think of that being conservative. But then the experimental results are really strong. So I'm wondering, do you expect that to be true in other settings too, or is there some reason that it doesn't matter so much getting the confidence bounds exactly right in order to get strong performance in practice?
Oh, you mean the decay rate that we have, like the kappa term that we have, because theoretically we have this kind of like 1 plus gamma times kappa inverse, 1 plus gamma times P max inverse.
Yeah, actually, even more generally, I mean, the whole CNF function has,
Yeah.
a 6 in it and a p-min in it, and things that show up in bounds. And sometimes when those show up in bounds, if you actually apply the algorithm, it doesn't work very well because you're realizing the bound. But in your case, when you apply the algorithm, it does work well. And I'm wondering if there's some reason that stuff didn't drive performance.
I see. I feel theoretically we have this Pmax is kind of unavoidable, but empirically, yeah, that's a good question. That yeah, in terms of theoretically, it's a poor bound in the setting, but yep, actually we in the empirical that we are trying to compare with the two baseline, which is the pure like model based and pure weighting based, and the other is magic. And we do not show any, which I also do not have experiment on, is that how this estimator like really compare with the oracle estimator in this set. So I'm not sure what's the gap for that one, which is also not shown here. So I'm not sure whether that gap will be large or not, but the current experiments show that it's only better than the existing baselines. That's a good question. Yeah.
Yeah, I guess like a simpler way to ask that question is that in these experiments, what were the confidence intervals that you were using? Were they also based on this Pmax factor, or were you using some tighter confidence bands like empirical Bernstein maybe?
Oh, yeah. So I'm just using standard deviation, like the empirical like variance. So it's not the exact like the confidence bound that we're showing theoretically. So that might be a reason here, but I think theoretically in the worst case, we should suffer from this Pmax here.
Right, but that's essentially like using empirical Bernstein, and that can be justified, right? So that you're really just using like the Pmax, well, not the Pmax, but right, the actual importance weight ratio squared in the confidence bound, and then I guess in empirical Bernstein, all that you have to add is an additional term of Pmax over n, and that is the same for all the intervals, right? And that does not change what the algorithm does.
Yeah.
Yeah, so that
I think
sounds legit to me.
It does sort of nullify my question, I think, a little bit. Yeah.
So wanted to return to my previous question just a little bit. If you go to the last slide, right. So for example, you know that slope doesn't address how we choose among different estimated classes. Is that really true? And also the next point as well, that slope doesn't address the estimator selection within a class for which we have no idea how bias variance changes. I mean, you can still run the procedure the way I described it, so that you compute the confidence intervals. You order these things in decreasing order by the confidence intervals. You run your procedure. There is a bound that holds for it. We don't know how good that bond is, but it's like you're guaranteed to have that. So in a way, yes, it addresses, and no, it doesn't address. Maybe that's going to be your answer, because we don't quite know how good this is, but you can still run it, and that's really great, right? Like you have a procedure that you can just run, and but it seems also to work well. And later on, we can worry about whether in a specific scenario, this is really a procedure that selects the best for that scenario or not. But in a way, it seems to me that the procedure is just universal. Am I missing something?
Oh, I see. In this case, are you trying to infer the population variance, the population variant of this monotonicity from the empirical version?
Yeah.
And if you yeah, that's the good point. I think it works.
Cool. I think it's great.
Yep.
Yeah.
I guess the problem is if you throw in something that's like isn't how this B of I is defined. Like I mean, there's no free lunch, so where do you run into the problem? I guess if you threw in something that was junk, like high variance, but
yeah. So maybe if you apply this in an hazard way, then you end up with some really bad choices, despite the fact that you have some guarantees, but those guarantees are so loose that it doesn't make any difference that you have them, because the bias will be pushed up, right? Like if you yeah.
Yep.
Right, so the method itself is expected to work still in this adjusted way that Chao was suggesting, so it should still be fine, but maybe the theoretical guarantees are not going to be so meaningful.
You still do have guarantees, just that maybe it's not only the theoretical guarantees are not useful, maybe the method is not useful in an unrestricted setting. You can run it. You get this guarantee with this modification of like how do we define the bias. But well, as Dan says, there is no free lunch, so there has to be some, like, it just can't do a good job across the board, because nothing can. The question is, maybe you could formulate this question like, okay, how do we know when not to run this procedure?
Yeah, well, I guess another way of asking that question is, well, what can go wrong, right, if the assumptions are violated? So if, well, say I can order my estimators in a way that the confidence intervals are indeed shrinking, But what happens if the assumption on the bias is validated? For example, if my first estimator has amazingly small bias, so what happens then?
Yep. I think this kind of like a procedure, it's kind of assumed that when you have like high variance, you typically have like small bias, but it may come in the case that a kind of like estimators, a kind of class of estimators is like, in terms of bias and variance, is all better than the other class. So in this case, even though you're ordering like variance in a, like say, decreasing order, your bias is not necessarily increasing, or you cannot get a sharper bound on the, like increasing on this. So you can also put some like very loose bounds, say like constant stuff, but in that case, it's definitely not worse. So I'm thinking that it's mostly suitable for the case where you modulate this kind of like trade-off like naturally, but in the like in any like non-restricted setting, it may become the case that you actually do not observe their trade-off. There may be one class of estimator this kind of like dominate in both terms of bias and variance.
So if you have something that is dominated, you need to take it out yourself, kind of.
Yeah.
But right. So to add another twist to my series of questions, so we could do this reordering based on the confidence intervals, but maybe there are some reasons not to do this. And then the question is, how do we know like that whether we should do this reordering or not, based on the empirical weights, and when to do it? Is there a way to somehow reason about this? Because I imagine sometimes it's not a bad idea.
Yep. I'm feeling this kind of like ordering by empirical variance. It makes sense as it like may serve as a good surrogate for like it also like maybe with high probability it gives you the like the trend for the true like confidence. But the thing is that I'm kind of worried about how you can infer like the bias upper bound in the setting. So this is the main issue there. If your like set of estimators, they definitely modulate this bias and variance trade-off. So maybe with high probability, like you can say that you can observe bias also have decreasing trend. If you know that this set of estimators, they have like this kind of trade-off. So I think it go back to the previous question. That is, I think the main issue that is the what kind of information you can infer for the bias upper bound.
In non-parametric stats, do people apply Lipsky's method for things that are like two-parameter families? Or, I mean, so sort of I can now see how it works for something like a bandwidth. But are there kind of other examples of classes that have this ordering?
I think in the original paper, as far as I remember, it's one is the smoothness parameter, the other is I think it's, let me check it. I'm not sure it's.
We do have a question from YouTube. Directly was asking, it seems slope is a hyperparameter selection scheme. How is it directly comparable to the other off-policy estimation estimators? I guess maybe the question is empirically, how did it compare? But I guess you had a bunch of results for empirical comparisons to other OP estimators. I don't know what Derek might be thinking about besides what you presented. Maybe he can clarify. But well, I asked him. So what do you say? How does it compare? Is it comparable to other OP estimators?
You mean this selection procedure for different OP estimators, or so I didn't get the question.
I guess maybe the first part was that, okay, it's like a hyperparameter selection, and then people have been doing hyperparameter selection. These are the means maybe, and like, okay, how does it compare to those?
Oh, you mean for general hyperparameter selection technique in the setting, or?
Maybe you could split the data, ignore the bias, whatnot, do cross-validation.
Yeah, I see. I see. So, yep. So in that case, I think it will prefer more for the direct method approach, because it's, if you ignore, it's very pretty optimistic about bias. And the other like regime of the method is that people trying to do this bound minimization, which you're trying to select the hyperparameter, which in the cross-validation set give you the mean like estimated MSE, a bound on the MS on the upper bound on the bias plus empirical variance. And so in terms of the theoretical like guarantee that those kind of method, they can only compete with unbiased estimators, but like slope, like they are trying to compete with the like best like estimator in this set in terms of this error bound. So this could even compete with bias estimator. And for the previous like bound minimization approach, they can only compete with like unbiased estimator, which maybe do not that like ideally, especially in the small data regime.
Can't you bound the bias? If you have a bias estimator, isn't the bias part of the bound on the law?
I mean, oh, sorry, I didn't hear that clearly.
Sure, I haven't thought much about this, so this might be a dumb question, but if you were competing, if you were trying to maximize the quality of the lower bound on the value you get or something, and some of your estimators were biased, but you have a bound on the bias, is that not feasible?
So in so you mean you have an upper bound on the bias?
Yeah, like your results, you
Yep.
showed upper bounds on the bias.
And you want to use this upper bound for the bias to do direct like minimization, or?
Yeah, to minimize the, I mean, so you gave bounds on the quality of a biased algorithm. Yep. So you could, in principle, minimize those or maximize those bounds, depending which way you.
Yep. But if you have a very good bias bound, that maybe work, but because like our procedure, it do not relies on, even though have a loose bound, you can still apply like slope. But the theoretical guarantee is that it compete with the any like the best like possible upper bound. So the bound minimization approach may be affected by the loose bias bound, but our approach may not. If you
Makes sense.
If you like in hindsight, you have like pretty sharp bias upper bound.
You're saying the bias bounds we actually have are not something you want in the algorithm, kind of.
Yep.
Makes sense. Well, that's good. Because one more like a fluffier question. Do you know that there's another algorithm called slope? in the stats literature.
Oh, yeah. Is it like in the high dimensional, like in the
Yeah. I
I
mean,
think it's relative
it also
structure,
has
right?
oracle inequalities and stuff. Is there any connection, or is it just the?
Yeah, I think that I didn't read that paper, but I also saw that name like accidentally. I do not like see any connection there, but I think it's just a coincidence in the name.
So in the chat, Tuan had a question that I think may be interesting. So Tuan, do you want to ask a question if you're still here?
Yeah, maybe my question is a bit dumb because I'm working on the MCTS where I use like a power mean estimator for the value estimation in the tree. And the thing is, the estimator is the bias is increasing when the power constant is increasing. And I'm not sure about the variant, but so I see the algorithm in this method is that we have kind of like the eta is like a fixed set of the eta, and also so the question, and we find the best eta for the parameter estimation here, and the question is for that like power mean estimator, can we also do the same method or like for the value estimation in general, maybe in the tree in my case?
Yeah, I feel if your hyperparameter, like naturally they have this kind of like monotonicity trend on the, so you say that you can like theoretically like justify the monotonicity like in the bias, but you are not clear about the variance term.
Yes.
I think in that case, like Chabas comments may work there, that you can like, if you know the exact ordering of the bias, you can check empirical variance to have like rough idea about how the confidence looks like in that setting, to see whether this like naturally have this kind of trade-off. I think if this is the case, the procedure may work. Yep.
Yes. Thanks. Yes.
Yep. Thanks.